Ta la 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 la. Ta la 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 la. Ta la 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 la. Ti la 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 la. Nothing. Waiting for a signal. Waiting for a signal. Is this the right one? Let me open it maybe with this thing. Ta la 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 la. Ta la 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 la. Oh, we have an audio. Okay. Mm, good coffee. Very good coffee. Hey, hamburger and fries. Everyone is here. Okay. Hamburger and fries. Everyone is here. Oh, we have an echo. Let's check why we have an echo. Audio. Well, echo cancellation is on. Oh, because I didn't shut down my mic check. Okay, so well, I see. Okay, I need to do two things. I need to debate. I need to debate people. Yesterday we had a good debate, but we didn't record it. It was about Israel and racism. Really interesting. Basically, between myself and Judas. So um, let's see. Let's invite Judas. Judas. Let's talk. I don't know. He might be working or something. He works. Yeah, he's a hard worker. Who else is interesting that has come aboard lately? Where's Lily? Oh, there she is. Who else? Zach Andrew. Well, he's offline. Who else? Who else can join us? La 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 la. What? These are the only members? Aren't there like many members? What is here? Notify everyone online who has permission to view this channel. Really? Uh, let's talk. Okay. Okay. Look, I just want to say my pronouncement. The most important. So I was thinking, I'm thinking about conducting a Michelson-Morley experiment vertically that will succeed. So first, I seem to have a solution. I mean, I have many solutions, but now I can fit it in a lab with normal equipment. Just it's gonna be. It's not normal. It's like we would have to build a rig, a rotating rig, and I'll explain it. Let's talk about the simplest, the cheapest, the most affordable way of conducting the Michelson-Morley experiment with a positive result. How Michelson could have gotten it right. Okay, so let's draw. Let me go and draw whiteboard. La 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 la. La 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 la. La 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 la. All right, so this is today's stream. Okay, that's from yesterday. Now let's create a new one. So this is going to be. So this is going to be. It's a 1,000. Let's call it the 1,000 mirrors rig. Mirrors rig. And let me explain. So, let me introduce the problem from the beginning. I'll introduce the problem, and then you will see the solution. So the problem is the original. Let's start from the beginning. So here is ground level. Undo. Here's the ground. This is the original Michelson-Morley experiment. So Michelson, they thought, okay, the ether exists, otherwise light couldn't travel. That was obvious to everyone. That comes out of Maxwell's equations, and which comes out of experiments. So experientially, and we know light is a wave. Light must travel even without Maxwell. We know that light behaves like a wave from the Young experiment. With the double slit original experiment, that we got interference pattern between light rays, then we know light behaves like a wave, which makes sense. It's fine, it's a wave, all right. So if it's a wave, it must be traveling through something. Okay, so that thing must be everywhere. Okay, that's no big deal. So we can't feel it, but there is a field of something, they called it the ether, through which light waves at, they discovered, about 300 million meters per second, really fast. Fine. So they said, okay, but we don't know how fast it's going. And this is where they didn't think through what is this ether and what more can we predict about it. They just said, okay, that's it. Light must travel through it. Let's go find it. If they would have first, paradoxically, forgotten about light and just thought about why does an apple fall from a tree, then you would have come up with a theory of gravity that says there must be this liquid that is flowing into massive particles, such as the Earth. So there's this flow of liquid, and it's flowing through us right now, and that is dragging us into the ground. We can't see it for some peculiar reason, but there is no other explanation. That's fine. And they would have said, okay, oh, and this liquid, and we also know that light must travel through a medium. Oh, that could be the same liquid. Why not? And then they would have gone back. These are the steps I went through, and then they would have gone back to Newtonian gravity. And Newtonian gravity, again, is from experiments, because Tycho Brahe took notes of the planetary motion. Kepler reduced it to basically a law of nature, equal triangles over time area thingy. And Newton deduced the inverse square law from that. Now, if you think about how gravity should work as a liquid flowing into Earth, you would also get the inverse square law, as Professor Leonard Susskind demonstrated in his general relativity course. That's very straightforward. That's expected. So everything fits. So then they would have said, okay, so that's it. Okay, the next thing is to say, well, how are we moving through this fluid? Oh, they would have calculated the speed of this fluid through the Newtonian field equations. You can reduce Newton's gravitational force equation. If you put ma equals gmm over r squared, the m's drop out and you just get an a equals gm over r squared. That's a field that's a vector field equation of acceleration. Basically, the curvature, that is what Einstein would probably call curvature. That's what normally we call, I think, whatever. And from that, you can deduce the velocity vector field equation, the Newtonian gravitational velocity field equation of a test particle. Then you place a test particle at infinity and let it start accelerating towards Earth, towards a point mass in an empty universe, where the point mass has, and then you want to see the speed of this test particle at radius, the Earth's radius. And you get about 10,000 meters per second, which is what I got. So that's the speed of a test particle of any mass, even close to zero, as close to zero, as arbitrarily close to zero as you want. This is completely logical. There is no issue. I'm not saying anything that is illogical. And this flow of test particle, that means then the next step is to say, okay, so why are these test particles moving? What's dragging them? Well, it must be some invisible fluid. For some reason, it's invisible. We don't know why yet. But this invisible fluid is dragging everything into massive particles. We don't know what happens to this fluid when it hits a massive particle. It looks like it disintegrates. We don't understand it. Where does the new liquid come from? It looks like very quickly the universe should run out of this liquid, so it must be getting refilled somehow. But fine, that's probably dark energy, right? That is basically dark energy, the refilling of this liquid. And then you would say, okay, so it's moving through us right now to about 10,000 meters per second towards the center of the Earth. But if this liquid is flowing and it's filling up space and everything gets dragged by it, so how are we moving through space if this liquid is in the way? How do particles move? And then you also think, oh, well, so at this point, I came to the conclusion the particles cannot move through this liquid. It's too rigid. This liquid is getting too much in the way. So what if a particle, well, a particle has to, in my imagination, I said right away, oh, then a particle must convert into a wave. Wait, let's just make it a wave. There is no particle, just like quantum field theory says, as far as I know. So there's this field, so there are no particles, there's only waves. So we're just made up of waves. We're just waving through this medium, which is, right, that's the same medium that everything is waving through. Oh, and light is a wave, as Young proved. Oh, then fine. Then just like light is a wave in ether, light is ether wave, well, so is everything else. All of our reality is just ethereal waves, waves in the ether. We are creatures of ether. We're just ether waves. We're waving through the ether. And with the Higgs mechanism, everything fits. The Higgs mechanism, gives slows down these waves so they look like particles. They look like they have mass. The Higgs mechanism. So this is the ether. So at this point, you would say this. You could have said many years ago, like during Michelson-Morely, they could have said this. Newton could have said this. Newton could have thought about all of this. Anyone could have thought of this. I'm not introduced, right? I mean, Young proved that light is a wave, so we had to wait for Young. When did Young prove light is a wave? When did Young prove that light is a wave? This is such an intricate story. I love the beauty, how everything fits, all these details. It's such a beautiful story, unlike, I would say, very much unlike how physics is told. Whenever I hear stories about physics, the evolution of physics, well, it's very, yeah, I guess it's the same. Okay, so this is 1801. This is 70 years before I mean, this is 70 years before the American Civil War, and Michelson-Morley's right after the Civil War. So this is basically 70 years before Michelson-Morley. Michelson-Morley knew already. Okay, okay. So Newton couldn't have done it. Newton didn't know, could not have known that light is a wave. Right before this, they didn't know light is a wave. What they didn't think about. I don't even think they had a wave theory. When did they come up with the wave equation? Wave like wait, you need to see this. So when did they come up with the when did they come up with well when did they understand wave mechanics? Physicists understand wave mechanics. When did physicists understand wave mechanics? 1920. No, no, no. This is quantum wave mechanics. No, no, I'm talking about wave mechanics, not Schrodinger wave. No, just wave mechanics. Not quantum mechanics, just wave. Like the Doppler effect, just wave mechanics. 1926. No, 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 no. Not Schrodinger. Wave particle duality. No, 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 no. Just wave mechanics. 1923. What is going on here? I just want water wave, air waves, mechanics of waves. Oh my God, why does it keep going back to such darkness? I mean, to such light. Why can't you remember to be dark? How difficult is that? Let me try and log in. Hold on. Share this. Let me try and log in. I think I've tried logging in before. It doesn't remember. Yeah, but this is Brave. I don't think Brave remembers anything. Join. I don't think I've ever joined Wikipedia. Okay, I need to join Wikipedia, I guess. Okay, I'll come back to this. La 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 la. Give me a second. Give me. Okay, okay, okay. Hold on, hold on, hold on. There you go. Okay. So what's the story? In physics, mathematics, engineering, and related fields, a wave is a propagating dynamic disturbance, change from equilibrium of one or more. Okay, give me a year. When did you realize this? Is there a year on this? Maxwell's equations. When is Maxwell's equations? Hmm. When did Max? I need like a timeline of all the big names. It's everyone wants to live in the pantheon of the big names. It's so great, like walk around saying, "I'm a big name." How does that song go? I'm a big shot. I'm a big shot. I forgot. There's a song that I love. The song that has those words. Anyway, let me check. Let me check. Let me check. Discord. We're alone. No comments. One person watching on the YouTube. Let me check audio. Mic check. La 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 la. Good. Audio is good. Okay, let's continue. Let us continue our research. I just want a year. Give me a year when they started understanding waves. So I need a history, mathematical description. Just give me the history, the hysterectomy. Like, yeah, differential wave equation. When did. Wait, somebody's talking to us. La 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 la. Oh, cruise ship. Jesus Christ is there for legal reasons. Okay, here. Jesus Christ is there for legal reasons. That's so funny. All right. Okay. Let us continue. Cruise ship is typing. Why? Cruise ship is a good person to talk to because we don't want to admit natural law has failed us. What do you mean by natural law? He had good questions. Some of my best like presentations have been with him, with his questions. He asked really good questions. Anyway, this is a differential equation of what? What is this? Well, there's time and space. One, two, three. This is the second derivative. This is the curvature. This is the acceleration. La 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 la. I don't right now. I don't want to go into the math. So wave in elastic medium. Yeah, I love math, but I just want the history, amplitude, and modulate. Where there's no history, special waves. Oh my god! Let me just magnify this because I'm breaking my back. Plane waves, kind of wave. I don't care. Standing wave. I don't care. Solitary wave. I don't care. Physical properties. I don't care. Wave velocity. I don't care. Transmission. Isn't there a history of when everything was discovered? Polarization. Really fascinating. Wow. Well, Newton knew about this, but he didn't think it's a wave. He thought it's particles. I don't know why. This is a wave in a string, water wave. Wow. So a particle. Wait, so the water is moving? That doesn't make any sense. You can have this in a tub where the water is not moving, so why would you say this? It looks like this particle keeps moving. So if this particle moves, something at the bottom maybe moves back. But that's what they're showing. But this particle must be moving. I don't know. Okay, body waves, seismic waves, shock waves, shear waves, electromagnetic waves. This is the worst way to show an electromagnetic wave. That is not what it looks like. It's a three-dimensional sphere. You can say that this is a cross-section of the wavefront. I mean, this is never mind. We're not going there. Quantum mechanical waves. Yeah. Gravity waves. So I'm just looking for when was everything discovered? When did they come up with the okay, so they couldn't have had a differential equation before Newton. So this must be after Newton. Newton came Newton could have used basic differential a basic differential equation. I don't think he had partial differentials. Maybe he did already. Maybe he came up with all of calculus, geometrical calculus, like analytical calculus, plane wave. Founders. Oh, modern. No, why don't you show me the founders of the wave mechanics? Anyway, this is useless. Why is it light again? And now you can't choose dark. Hello, darkness. Smile. I don't know. Okay, not the history. Okay, physics, mathematics, equilibrium, quantum, periodic frequency, waveform, wind wave. Okay, waving, wave, disambiguation, wave, literature, music, fictional, music, bands, albums, songs, radio, television, business, politics, sports, technology, vehicle, other. Wait. What about science? Not to be confused with waves. A wave is a disturbance. Yeah, we just saw that. There's no history. There's not a single year mentioned in this entry. There's no year. I just kept looking for a year. Show me a year. It's freezing in here. Show me a single year. When did they come up with any understanding of any waves? I don't see any years mentioned. Wave spectrum. Wave families. And there's no table of contents for this entry. This article is about waves in the scientific sense. For waves in seas and lakes, see went for the human hand gesture, see waving. For other uses, see wave, disambiguation, and there's nothing there. In physics, so this is useless. So we need to just look it up. When did Young prove? That's 1801. So let's ask, when did they first come up with a wave equation? When did physicists understand wave mechanics? Yeah, that was the original question. This is not it. No, physicists. Is this how you spell it? Physicists. 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 Is this how you spell physicist? Isn't there a C somewhere? Okay. Oh yeah, there's a C. Physicists. Yeah, too many S's. When did physicists understand classic wave mechanics? La 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 la. 1920s. No, 1920s is non-classic. Why would you? Okay, 1910. Bohr. No. No. Classical mechanics. We gotta go here. La 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 la. Classical mechanics. Okay. So let's look for classical mechanics. Force is equal to the change in momentum. Force is equal to the change in momentum. That's actually mass times acceleration. That's interesting. That's an interesting way of saying it. Okay. So it can. Okay. So let's look for wave here. Classical approximation to quantum mechanics. What about just class? Just give me classical waves. This is quantum mechanics, Planck's constant, history, wave. This is the last one. Here it is. Okay, the wave interference phenomenon. Newton had previously invented the calculus. However, the principle was formulated entirely in terms of long-established geometric methods. No, Principia, not the principle. The Principia, his book, was purely based on geometric methods. Yeah, which is, I think, people say it's because they wouldn't have understood him, but he invented calculus in order, I think, to do his work. So he would have used it if he really trusted it. I think he didn't. My intuition is either he didn't trust calculus. It seems like an approximation. It seems like something is wrong with calculus because of the infinities. Everything has to do with infinity over there, or infinitesimals and limits. It's like something feels awkward about it. Whereas with geometry, I think geometry is just more intuitive. So if I can prove something with geometry or with calculus, of course I would rather use geometry. Geometry you can visualize. You don't need to believe some calculus derivative or integral. Who knows where you went wrong? With geometry, it's a much better proof. La 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 la. I'm just looking if we have any comments or questions. Okay. Mm-hmm. Let's continue. So, geometric in emulation of Euclid. I don't think it's in emulation. People, I mean, I need to look into Principia. What did Newton say about his decision to write Principia one way or the other? You need to see what the person wrote. And even what the person wrote doesn't mean that's the truth. People don't know why they do things. When a person says, I did this because of that, that's a theory. They don't know why they did that thing. It's unknowable why we do things. Unless you have an fMRI in real time, or like me, I'm recording everything I'm doing, everything is being recorded, then you can really go back and see exactly when I thought of something. Anyway, I'm still about to present to you something that I just came up with, so we need to go back to that. So Newton and most of his contemporaries, with the notable exception of Huygens, worked on the assumption that classical mechanics would be able to explain all phenomena, and Huygens, including light. Huygens disagreed in the form of geometric optics, even when discovering the so-called Newton's rings, a wave interference phenomenon. He maintained his own corpuscular theory of light. Okay, what is Newton's rings? Newton's rings is a phenomenon in which an interference pattern is created by the reflection of light between two surfaces, typically a spherical surface and an adjacent touching flat surface. It is named after Isaac Newton, who investigated the effect in 1666. I don't think a phenomenon like this needs wave theory, but I guess because you can view it as corpuscular, like you can get this phenomenon that we see here. You can get this even with particles. Particles cascade. Particles could give you this formation. It looks like something, unless you can show that it's waving, then it's more difficult to use particles. Okay, let's go look at Newton's rings. Um, if he would have thought a little bit more about how gravity works, instead of just he finished. I think the problem is he became famous, and he left physics, and he started doing chemistry and what do you call that? Chemistry of gold. So he stopped doing physics basically. He started doing other things, finance and mint, working for the king. And that we basically lost him once he started doing other things. We lost physics, lost him, or he lost. So he didn't finish his theory of gravity. He didn't. He just started by asking a question. He asked a good question that even Einstein never answered. That how could you imagine the force of gravity being mediated by nothing? That doesn't make any sense. Okay, so what's the story with this thing? Let's I need to see a video of what this phenomenon was. Why did he think? But I don't want to get distracted. My only question is, when did they know? When did they know light is a wave? If Newton wasn't convinced that light is a wave at this point, then this is 1666. Forget it. I don't care. There's not enough information. The phenomenon was first described by Robert Hooke, 1665, a year before micrographia. It, didn't he invent the microscope? Who acted as a physicist, astronomer, geologist, meteorologist, architect. He is credited as one of the investigate living things in microscopic scale. The first thing he looked at, of course, was his sperm. So, because they expected to see little people. Its name, its name derives. Its name, whose name? Derives from a mathematician, Sir Isaac Newton, who studied the phenomenon in 1666, a year after. What's going? Okay, never mind. Forget it. Forget it. This is really interesting. The history of science is a fascinating story by itself and is critical. It is critical to, to get a feel what came out of what and why did you think of that, and like to really get a feel for the evolution of science. Okay, let's get back to work. Okay, so we were here and we were talking about the beginning. The beginning. So in the beginning, in 1886, Michelson and Morley said enough is enough. This is 80 years approximately after Young's experiment. Light is a wave. Good. So it's waving through something called the ether. So Michelson and Morley, I think Michelson was the brain, Morley was the assistant, if I'm not mistaken. So Michelson and Morley, so Michelson invented the interferometer, and they built a big interferometer, very stable, perfect, excellent interferometer that cannot detect a vertical motion of ether. If it goes right into the earth, right through into the earth, it will never detect it. That's what they did. So, okay, they discovered that it's, well, they did whatever they discovered, fine, the null result. But as I know now, this null result, even if they would have done it vertically, they would have gotten a null result because the ether is moving way too slow. So they thought the Earth is flying really fast through the solar system. They thought it's got to be a significant magnitude. Let's see, how fast did they expect it to be? Because they just said, okay, it must be stationary in reference to the sun. So let's see, how fast is Earth going around the sun? So how fast is Earth going around the sun? That's basically what they should have considered the speed of the ether to be. So it's 30 kilometers per second. That's 30,000 meters per second. That is significant. That's 30 times faster than it is. But it's not going horizontally, it's going vertically. But they didn't, okay, so it's still very, very insignificant. I mean, even if they had this number, so they should have expected a null result. If they knew this calculation, they should have expected a null result. That's not fast enough relative to the light. And Lorentz already knew about gamma, so they knew that the time dilation is not enough. A 1 meter device interferometer would have given you a null result. So what's wrong with these people? Didn't they do the calculation before they wasted their entire life? This is incredible. People invest a lifetime in an experiment that they could have done on a piece of paper and seen that it's a null result. We saw yesterday. This is this is insignificant next to the speed of light. It's not, it's whatever. It's not enough for a 1 meter interferometer unless you have unless you're doing back and forth, which is what I'm about to explain to you. Let's look at their original equipment. michaelson-morely original equipment. Show me the picture. La 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 la. La 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 la. Michelson and Morley's interferometric setup. That's the best picture we have. I can barely see anything. What are we seeing here? What are we seeing? So it looks like it's in a basement because they wanted to be on the, they wanted to minimize the vibrations. That's good. So it looks like this looks like a mirror. Where's the light source? Why is there two things in the middle? There should be only one thing in the center. I don't understand. This looks like the display. An interferometer should only have 4 edges. An emitter. So if this is maybe a mirror and this is a mirror, maybe this is the detector and this is the mirror. We need 2 mirrors, a detector and a display, and a half mirror at the center. So this could be, and the 2 arms. This doesn't look like a square table, but I have to assume it's a square. It doesn't look like a square, but it must be a square, but it doesn't look like it. But it should be. I think it does. I don't think it has to be. Anyway, I can barely tell what's going on here. But so the fact that there's 2 things at the center is bizarre. I don't understand what's going on here. And why is there things here? Yeah. Okay, whatever. Okay, I don't understand this image. I saw another image. Depiction of the concept of the ether wind. Right, so did they do a calculation of the speed? Like, what's your theory about the wind, the ether wind? What's luminiferous ether or ether was the postulated medium for the propagation of light. It was invoked to explain the ability of the apparently wave-based light to propagate through empty space, something that waves should not be able to do. Something empty space is something that waves should not be able to do. Of course not. That's by definition impossible. Definitionally. The assumption of a spatial plenum of luminiferous ether, whatever. So they should have done a calculation, seeing the speed of the Earth, maybe even the speed of the sun through the galaxy. I think they already had, in 1886, they had a notion of a galaxy. What did they expect? Here it is. This is the setup. This is Michelson's 1881 interferometer, although ultimately proved incapable of distinguishing between different theories of ether dragging. Its construction provided important lessons for the design of Michelson-Morley 1887 instrument. So this is Michelson 1881. Why does he have two mirrors? Okay, I know why. So one is a beam splitter and the other one is a mirror. Because on the way back, you don't want, right, that makes sense. So you need a beam splitter, which is half a mirror, and then a full mirror in order, yeah. So I guess these are the mirrors. And then, I don't know, is this the one of these two? One is the emitter. So I'm assuming this is the emitter because it looks like it's aiming at this guy, which is the splitter, because this looks like it's on the way back. Wait, maybe the opposite. I don't know. I don't know. What is alpha or A? We need to look. It doesn't. Okay, I mean, it would be interesting to know, to understand his. Oh, did he register it as a patent? That's interesting. So maybe it's a registered patent. Anyway, Michelson had a solution to the problem of how to construct a device sufficiently accurate to detect ether. We need to read what he thought. Why did he think he's going to detect it? He needed to have known the speed. If you know the speed, if you assume his speed, based on that, you build your device. You need to assume something in order to discover it. What's your assumptions? What are yours? Tell us your assumptions. Tell us about the plan. Anytime you want to do a test, you first have to write a test plan. What are you planning to test? You need to tell everyone. You need to tell yourself. What are you planning to test? What are your assumptions? So for Michelson-Morley, the Michelson-Morley experiment was an attempt to measure the motion of the Earth relative to the luminiferous ether, a supposed medium permeating space that was thought to be the carrier of light waves. Thought to be. Yeah, the experiment was performed between April and July 1887. April is the 4th, April. So let's start with April. Just 3 months. By American physicist. This was probably the only American physicist at the time. I don't know if anyone was doing physics in America. Anyway, these are okay. Anyway, American physicist Michelson and Edward Morley. So that's what he looked like. Albert Abraham Michelson, FRSE, was a Prussian-born American physicist of Jewish descent, known for his work on measuring the speed of light and especially for the Michelson-Morley experiment. In 1907, he received the Nobel Prize in Physics, becoming the first. So he received the Nobel Prize for what? And Morley was an American scientist known for his precise and accurate measurement of the atomic weight of oxygen in the Michelson-Morley experiment. Okay, this guy is not no slacker. Okay, these guys were not slackers. So why did they fail with this experiment at what is now Case Western Reserve University? So that's where it was. That's where they. This is in Cleveland, Ohio. And published. Isn't this where? Okay, published in November of the same year. Jesus Christ! The experiment compared the speed of light in perpendicular directions in an attempt to detect the relative motion of matter, including their laboratory, through the luminiferous ether, or ether wind, as it was sometimes called. The result was negative, that Michelson and Morley found no significant difference between the speed of light in the direction of movement. All it means is it's moving too slow. But what did you expect? I mean, the Earth is moving very slow. Everything is moving very slow compared to the speed of light. Your equipment, just do a simple calculation. Why would you expect any result in any direction? It's hopeless. Of course, you get a null result with this equipment. The equipment is not accurate enough in any way. I mean, even if you would have done it vertically, you get a null result. Through the presumed ether and the speed of light and the speed at right angles. Okay. This result is generally considered to be the first strong evidence against some ether theories. In the history of physics, ether theories propose the existence of a medium, a space-filling substance or field, as a transmission medium for the propagation of electromagnetic or gravitational forces. Since the development of special relativity, theories using a substantial ether fell out of use. While Einstein proposed it in 1920 in his lecture in Leiden, so why are you saying that? Are you ignoring Einstein? Is Einstein doing something means it's not like that, that's not considered whatever? I don't understand. And why didn't Einstein, if he thought gravity is ether, why didn't he write papers about that? Why only talk about it in a concluding remark in a lecture 5 years after GR? It's like he never really understood GR. And did he feel he understands GR? I think he was getting so many things wrong with GR. General relativity, GR, general relativity. I think he was embarrassed. I think it was he laid low. I think after GR, he felt embarrassed and he just kept quiet. So no, because when you keep quiet, no one knows you're dumb. When asked, he said, "I don't understand it." Right? He has a quote: "Since mathematicians invaded relativity, I don't understand it." So he kept quiet. And because he kept quiet, everybody thinks he's a genius. He was pretending to be a genius. So everybody bought it. They bought his genius. If he's quiet, he must be a genius. La 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 la. La 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 la. La 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 la. All right. Okay. So ether theories, as well as initiating a line of research that eventually led to special relativity, which rules out motion against an ether. Who says that? Staley Richard, 2009. Albert Michelson, The Velocity of Light and the Ether Drift, Einstein's Generation, The Origins of the Relativity Revolution, Chicago, University of Chicago Press. Okay, so that's what he says. This Richard Staley. Okay, I don't know who this guy is and why he says that. Okay, but Einstein didn't say so. Of this experiment, Albert Einstein wrote, if the Michelson-Morley, finally he's talking about it. I need to see more of what he says about it. If the Michelson-Morley experiment had not brought us into serious embarrassment, no one would have regarded the relativity theory as a halfway redemption. Albert Fusing, Albert Einstein, a biography. Jesus Christ. When did he say this? When did Einstein talk about Michelson-Morley experiment? When? Because in 1920 he already contradicted this. He said gravity is ether. Okay, when did Einstein... Okay, Einstein, let's take Einstein-Michelson-Morley experiment. Let's search Brave. Albert Einstein wrote, if the Michelson-Morley experiment. Okay, whatever. Sorry, Michelson. Okay, this is the Michelson-Morley experiment on Wikipedia. I just want to see what Einstein was. Einstein aware of the Michelson-Morley experiment? Yeah, that's what I want to know. Let's open this and look it up separately. The tale of a 1986 experiment that proved Einstein wrong. 1986, Silvertooth performed an experiment that seemed to overturn Einstein's theory of relativity. 30 years later, the mystery was solved. Okay, I don't care. This is Forbes. Special relativity. Did Einstein know about Michelson-Morley? Let's look it up. He just knew the name of the experiment, not any details. The experiment didn't play any role in the formulation of STR, Special Theory of Relativity by Albert Einstein. The context is taken from the book Special Theory of Relativity by V.A. Atonov Yuri, translated Ugarov, author. What is that? Oh, so this guy translated, this guy is the author. So it's Ugarov, I guess. Art. Was Michelson's experiment decisive for the creation of special theory of relativity? By an article by R. Shanklin, published in 1963, the following excerpt from his interview with Einstein, dating 1950. Okay, we need to know this. When I asked him how he had learned of the Michelson-Morley experiment, he told me that he had become aware of it through writings of H.A. Lorentz. What year? But only after 1905. Had it come to his attention. This is unbelievable. He wrote the paper before. This doesn't make any sense. Otherwise, he said, I would have mentioned it in my paper. That makes sense. So he didn't know about it. Wow, this is what I've been looking for all this time. Indeed, Einstein's 1905 paper contains no mention of Michelson's experiment or references to Lorentz papers. This is ridiculous. I mean, it makes sense. It's this the history of this entire of special relativity is so it's unbelievable. Such a mess. So he didn't know about the most relevant experiment and the most relevant stuff. He didn't know about Lorentz transforms. So he reinvented Lorentz after Lorentz. Isn't Lorentz? Didn't he talk to Lorentz? Einstein's 1905 paper contains no mention of Michelson's experiment or references to Lorentz. Yeah, but they didn't interrogate him. They didn't interview him about this. Unbelievable. You have to be a detective when you do physics or any science. That's my experience. People don't know this. When you actually want to study any field, you really have to become an archaeologist slash historian slash detective slash psychologist. You really need to, and you need to cross-examine every bit of evidence that you can put your hands on. And it's like people think there's too much information. No, there's hardly any information. There's hardly any information about anything. And it's really important to go back to the beginning because everybody else since then has been confusing the facts. People speak out of their tushies all the time, including the biggest names. They say it's people repeat what they hear, but they misquote, they misremember, they misunderstand. There's so I mean, talk about broken phone. It's the broken telephone game. So you always have to go to the source material. Always go to the source material, because you have to just assume everybody's talking out of their tushies. Everyone's talking out of their tushies. You need to get the source. That's why you need to look at the original pictures, at the original transcripts, at the original. Is it the original handwriting? You have to. You just have to. You have to. I mean, otherwise, you're missing context, and I mean, you're missing information. It's difficult to believe, but this archaeological. This is archaeology, or you call it whatever you want. Sort of archaeology. You have to dig up everything original as much as you can. Like this interview in 19. When was this interview? In 1950, published in 1963. This is, I've been looking for this. I need to know, what did Einstein know about Michelson-Morley? Oh, that's how you spell Michelson? It's not Michaelson, it's Michelson. I thought it's Michaelson. Probably was Michelson originally. So he's an American Jewish Prussian scientist. At this point, he's one of my favorites because he's better than Einstein, because he didn't forgo logic. Einstein just ignored logic, ignored intuition. Einstein was not scientific, and Michelson was scientific. But Michelson, I mean, was not a good experimentalist. He didn't write his prediction. You first need to calculate the prediction. You need tell us, what is your prediction. You don't run an experiment to to find something, to search. That's you shouldn't do that. That's You're going to get a null result. You're not going to know why. If you would have done the calculation, you would have seen it's going to be a null result. No matter what you do, it's going to be a null result. I don't care what you do. Even according to you, you should have gotten a null result. The equipment is too small. The light frequency is too big. So you're not going to get anything significant. Anyway, I got to go to the bathroom. Okay, let's take a break. I'm going to stop here. It's been an hour. It's okay. It's good. We're making good progress. I need to show you. So I was going to show you, and I want to show you, this is something I came up with, how to run a proper Michelson-Morley experiment that will give you results. The results that Michelson was looking for. So you will rotate it, and you will see an interference pattern, as many as you want, as many ticks as you want, with many mirrors. And this is why this drawing is called the 1000 mirrors rig. So the more mirrors you use, right? I'll just say it in short before we take a break. So the more mirrors you use, basically the greater distance you can cover in the same room. So you can use tiny mirrors, just tiny, tiny, tiny mirrors. You can have either a kilometer, like 1,000 mirrors over a meter, that's a kilometer, and you could do 10 of these. You can build these and stack these devices. It's going to be a big rig, because if your mirrors are big, but if your mirrors are tiny, if you can build a digital, like a robotic, you can build something robotic, because you don't want to do this manually. You want to do this with a machine. So you can build tiny mirrors, but you're going to have a problem with the laser. You're going to have to use an expensive laser, not a cheap $1. $1 laser is not going to last a kilometer. So you need a powerful laser. It's the laser itself, but you probably have a good laser like that in the lab. So the laser is not the problem, but over so many mirrors, you're going to lose focus. So I don't know what to do about that. So you need a super powerful laser and very accurate mirrors. So the mirrors are going to be special mirrors, very, very good mirrors. You can't lose focus. So, either that, or do it in space. If you do it in space, so I thought about that, but in space you're going to have another problem since you're rotating about Earth, and the speed of the rotation is about 7,000 meters per second. The speed of the ether going down is 10,000. So that's, similar, very similar numbers. Again, it's going to be very big. So even if you do it in space in orbit, it's going to have to be huge. The arm, because the difference between those two, I mean, I need to look at the, because the way the experiment, we need to look at the experiment because of the speed of the motion through the ether. So it basically cancels out the motion of the ether. So again, you're going to get a null result. It's very difficult to avoid a null result. So of course this is outside of the reach of Michelson, but it's really interesting. It's really interesting to think about. If you don't plan an experiment, don't expect to get anything but a null result. So he died not understanding how this could have failed. And all of science went down to crapper because of this. Now we live with the most corrupt scientific industrial complex possibly in the history of the universe. And this is all because Michelson didn't predict the results, didn't tell us what he's expecting, right? This is basic, what do you call the scientific method? Well, Bacon. This goes against Bacon. Bacon told you, you have to make a prediction. Make a prediction. You can't go just search nilly-willy. You got to make a prediction exactly what you're going to find. You would have seen it's not going to work. You would have seen it's a null result. I mean, the very fact that the Earth is rotating very fast is already an issue. How fast is the Earth rotating? That in itself, you need to take into account. I just thought about that. How fast is the surface of the Earth? Is the surface of the Earth moving? Right now, how fast, I mean, at the equator, let's say. So at the North Pole, you don't have this issue. So you need to conduct this experiment at the North Pole, like every other experiment. All experiments need to be conducted at one of the poles. So you probably need to go to Antarctica or something, or the North Pole. Probably North Pole is easier because you have zero rotation there. Oh my God, this is making this experiment so expensive. How? There's no way to avoid a null result. It's like, you need to think of everything in order to avoid a null result. There's so many parameters. How fast is the surface of the Earth moving at, let's say, the equator? And then we do maybe half of that for Ohio, Cleveland. How fast is the surface of the Earth moving? It's about around, let's say, approximately roughly 1,000 miles per hour at the equator from the Earth. Right. These values are consistent across the search result, indicating that the surface of the Earth at the equator moves at speed relatively 1,000 to 670. All right, let's say about 1,000. It's a ballpark. So it's 1,000. Okay, so it's a tenth of the speed of the ether. Not so bad. And if we're talking about Cleveland, it's probably going to be half of that, so 500. Okay, so it's not the end of the world. Okay, let's take a break. We'll come back and we'll continue talking about the proper. And we need to write this down in our, here. We need to write, I wish I could make this dark. So we need to write this in our document. We need to plan the Michelson-Morley experiment, because Michelson-Morley never planned his experiment. He never planned. He never told us his expected results. Michelson never told us. I need to look at his notes. is expected. What are you expecting? You want to tell us what you're expecting? No, then I don't know what you're looking for. All right, so there you go. And I was thinking about this. Even if I get a result, they're going to tell me, yeah, sure, that's just the curvature of space. They're going to go back to the same nonsense. Yeah, but they keep claiming that there is no ether because Michelson failed. But even according to them, Michelson shouldn't have failed. Because they agree light bends. Einstein said light bends. If light bends, then of course light is going to slow down. If you point it up. So the reason they're not pointing it up is because, well, they want to avoid the effect of gravity. But you're looking, but ether is gravity. So they're going to tell me that's not what I'm doing is not the Michelson experiment. You're not measuring ether, you're measuring gravity. There's like no way out of this. There's no way out of this except for telling people it's just not scientific. There's nothing I can prove. So it's just not scientific. If there's no way, right, the theory of relativity is not falsifiable. The theory of relativity or the detection of the ether is not falsifiable. If there's no way I can falsify your vacuum theory, then it's not a theory. It's not scientific. If you believe in waves propagating through a vacuum, okay, that's a theory. How can I disprove it? You gotta tell me how I can disprove your theory. You gotta tell. If you cannot tell me, you're not scientific. That's the end of that. You're not scientific. What do you want me to do? You're not scientific. That's the end of it. You gotta tell me how to. You have to tell me how to disprove your theory that light travels through a vacuum. How can I disprove it? If you're gonna tell me Michaelson-Morely, all right, tell me. Okay, Michaelson-Morely, what? No, don't tell me Michaelson-Morely. Give me the exact setup of the experiment in order to disprove your theory. If I do exactly these steps and get this result that disproves and this result proves, what is, you got to tell me the exact details. So the theory, the vacuum theory is unscientific. So we have the ether theory, but the vacuum theory is unscientific. We have the ether theory, and we must have the vacuum theory. Oh, this is heading 2? Whatever. The vacuum theory. Well, the vacuum theory is not scientific. Well, I've never heard of how to falsify it. Now, if you tell me that Michelson and Morley, what year was Michelson? When did he publish it? I think in 1886. So if Michelson, 1886, null result is evidence of the vacuum theory, that's fine. Then what would be of none null? But I can prove to you that that's not evidence. It's not. What was expected? I don't understand. What did he expect? Some wind? Some magical wind in some direction? Why not gravity as Einstein suggested? Oh my God, this is so unscientific. I don't even know. I'm like, I'm debating a 3-year-old at this point. Not even. I'm debating a pigeon. This is like when I debate people on Discord, they make more sense than this theory. The vacuum theory. It's not a theory. It's nothing. It's garbage. It's unscientific. No matter how you think about it, it's unscientific. There's not. I don't know what to say about it. It's like no matter what evidence I put forth, I need to know what evidence do I need to put forth and why. So you need to tell me. Did I? You need to tell me. You need to tell me what evidence I need to put forth to prove the ether model. You need to tell me that. And of course, give the reason. I can give you the model that explains, but you're going to tell me that's just the curvature of space. But that's not scientific. You can't talk that way. What is that? What does that even mean, the curvature of space? And you would say the curvature of space time. What the heck is that? It's nonsense. Anyway, I think this is a dead end. It's just a dead end. There's nothing you can do. I mean, I think we proved already everything. Anything we prove further. Like, I need to ask people. So the only way out of it is to just ask the experts, like the top scientists, what would they expect? My thousand, let's call it the thousand mirror. My vertical, let's just call it my vertical. My vertical, what do you call it? Interferometer. Results to be. The only way out of this is to ask the experts to calculate, to predict. They need to make a prediction. What would they expect my vertical interferometer results to be? They need to make a prediction. Of course they're going to say it's gonna you're gonna get interference. Then I don't know what to say. Then done. We're done. If you agree that we're gonna get interference, then that is. If they say that they expect an interference, then we are done. I don't know what to do at that point. Then again, I don't know how to falsify the vacuum theory. What's going on? Oh, Andrew, Mr. Check DMs. 1 second, let me check DMs. What does he say? La 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 la. How old are you? I don't disclose. Let's debate. The problem with Andrew is he disconnects. We can only have a very short debate, so it's never fun with this guy. It's always terrible. Like, we start and he talks and talks and talks and talks and talks and disappears. Every time. It's like the worst debate partner. Okay, we can stop here. I mean, I don't know. The point is, I don't know how to disprove the vacuum theory. It's so nonsensical because even they say there is a field permeating and a field and a field. Yeah, but these are quantum fields. What about a gravitational? That's a field. Everything is a field. But there is no ether. There's a field, but no ether. So what's the difference between the field and the ether? They agree that there's a field, but they disagree. It's called the ether. If there is a field, then why is it not the ether? A gravitational field gravitational field, then why is there no ether? That's how you spell ether. Anyway, you need to tell me how to disprove the vacuum theory of light. And they would say, no, of course we know there is no vacuum. Of course there is no real vacuum. The vacuum is a misnomer. Okay, then does light travel through a vacuum or no? No, of course not. There's this. So isn't that the ether? And isn't the ether flowing into the earth right now? You already agree that light bends. What else do you want? If light bends, that is the Michelson-Morely experiment. If light bends because of gravity, you know what? The rotation of the earth is the evidence, not gravity. The other effect. We need to cancel gravity and show that the rotation of the earth through the ether, we need that. Or even in space, that's what we need. We need to show that as we go around the earth, it's the opposite. We need to cancel the gravitational ether because they say, no, that's fine. But they don't account for the rotation. So that's what we need to show. We need to show that the rotation, the Earth's rotation through the ether, gives you an interference pattern. So we need to be even much more sensitive. We need to cancel the, oh my God, Jesus. But that maybe would prove it. So maybe we can show that when we rotate on Earth or in orbit around Earth, we can get an interference pattern or a positive result and that would finally prove. This is what I need to ask them. This they don't predict. And that would finally prove that we are moving through the ether. Wow. I think this they would never predict. I would ask them, okay, we will conduct it at the equator or whatever. And we'll cancel the effect of gravity. Now what do you say? We would run it horizontally. We would run it horizontally. That's how you cancel the gravity. Setup. Run the experiment perfectly horizontally in order to cancel the gravitational effect. Because the ether flows directly into the center of the Earth, and the Earth rotating is moving through the ether horizontally. Run the experiment perfectly horizontally in order to cancel the gravitational ether flow effect. So we're going to cancel the vertical, the gravitational vertical ether vertical flow. So we're canceling the vertical flow effect. So now as we move, we're moving horizontally through the ether. We just need to make it much more sensitive. Now make that much, much more sensitive because we are moving at about 500 meters per second, like in the middle northern hemisphere. So if you're doing it in the middle of the northern hemisphere, I wish I could just select northern hemisphere. 1 second, we have messages. Let me check messages. What? Okay. Check DMs. I checked. Andrew says, debate what? I'm not debating without judge. Okay. Can we at least debate that? Can we discuss that? Can we discuss it? I mean, let's discuss what is the purpose of a debate. Let's first discuss the purpose of our debate. Let's first discuss the purpose of our debate. And based on that, we can discuss the conditions. Okay. Because this is not a war, this is not a competition that you need a judge. Because we are moving at about 500 meters per second in the middle of the northern or southern hemisphere, So that's relative to the speed of light. So relative to the speed of light, that is, oh my God, I mean, that's like, that's 500 divided by 3. 1, 2, 1, 2, 3, 1, 2, 3. That is ludicrous. That's basically 300. Let's imagine it's 300. So we move to 0. So it's 1, 2, 1 with, we said we're going to remove to 0. So 1 million. So that's basically 1 micron. It's a ratio. Well, micron is not, it's 1 micro. It's not a micron. It's 1 micro. It's 1 millionth. It's 1 to a million. That is 1 to 1 million. So you need, okay, I mean, so that's relative to light, right? Okay, but it's doable. At least we don't need to rotate it about vertically. That's good. It's going to be rotated horizontally. That should prove it, because then it's not gravity. What are you going to say to that? That's the proof. So we're back to the horizontal. Unbelievable. This is such a roller coaster. Anyone following the developments here, this is such an emotional, such an emotional roller coaster. They're never going to predict this. This is going to be completely counterintuitive. I'm going to ask them, okay, I'm going to build this rig. This is very similar to Michelson-Morely, just that instead of one arm back and forth, it's going to be 1,000 times or 1,000,000 times back and forth. It's going to be tiny, tiny, tiny mirrors with a super powerful laser, super accurate mirrors. What are you going to say to that? And actually, we can build a very big rig. I mean, because it's horizontal, it could be very big. We can just go to some empty field and build a very big rig. So we can take a string. The problem is, we can build it with a string, We can go to a very big flat surface and just have a string, like a cable, and slowly rotate it, like build a huge. Can't be. I don't think it's going to be like it could be with a bunch of cars in the middle to hold up this thing. It's going to have to be. It's going to be a huge rig. So but we can build it. It's really simple. It's simple to build. It's going to be a huge operation in the middle of. It's like every time you look at these experiments, you're saying, why did they have to do this? I mean, couldn't they have done something simpler? Like, no, they couldn't. They couldn't have. That's the beauty of it. That's part of the beauty. Part of the beauty is you got to build these huge rigs to test for this edge case that nullifies this and nullifies that and nullifies that, and then you still get a null result, and you go back to the drawing board. Why am I getting a null result? Oh my god! I would have gotten so many null results if I would have at any point gone and conducted the experiments, either a null result or they would have told me, no, that doesn't prove anything. This is the same as what we expected. You fulfilled our prophecy. Oh my god. Okay, so we can build. I think this is it. So we can build a big rig. We can build a big. Maybe that's what I'll do in the next lecture. A big rig on wheels in a very large flat land, as close as possible to the equator. It's like you would ask, why is it? How is the equator relevant to your theory? My God, oh my God, it's so crazy. I would have never thought of this. Like if somebody would told me, even yesterday, even a week ago, this is how Michelson would have gotten a non-null result. This is the only way. I would have said, what? What are you talking about? What are you talking about? Yeah. It's going to be horizontal. Wait, we have a visitor. It will be. Who is here? Horizontal. Who is here? Who is with us? Andrew. Of course, you muted. Okay. Okay. So okay, we'll continue this. Let's stop here. Let's stop here. We'll continue after these messages. All right. Bye for now. Andrew, can you talk?